Hi, welcome back to AP Physics C, the Electricity and Magnetism course. This is again Unit 3, where we're focused on circuits. So the first three videos kind of laid the groundwork to get to this point. So we just basically introduced in some of the basic terms. And so now what we're going to do is now we're going to start looking at the different types of circuits. We're first going to focus on resistor circuits that are in series and parallel, and then we're going to dive into resistor capacitor circuits. Okay, so for one thing to know is that for you to have a circuit, you have to have a closed loop. Okay, so a closed loop is what's going to get that electricity to flow. All right, and then the way we look at it is there's two types of circuits. There's a series circuit, and then there's a parallel circuit. So series circuits are ones in which the current flows through a single path and encounters resistors along the way. The way I like to equate it is like running, around a track, right? So what that means is that the current is going to be the same. So I through I1 and I2, I ... that's always going to be the same. What's going to change is going to be the voltage. And simply the total voltage is going to be the sum of the voltage between those between the different resistors. Now, what we can do though is we can take those resistors and basically so let me go back and talk about parallel circuits. So a parallel circuit is like, you think about it like roads or like residential roads where you have many different paths to take. So in the diagram there, we have two paths. So what happens is it comes into the junction and then the current is going to split. Okay. And the way you think about it is on Black Friday, right? Everybody's trying to find the path of least resistance, which means it's the cashier that has the least amount of people. So everyone's going to split to find their way, but then they're going to meet up again to go out the door, right? And so that's what happens. The way you could think about parallel circuits is that the voltages are always going to be the same. The way you think about it is that it's a bunch of simple circuits put together, connected to one terminal, right? One battery. All right, let me put a line here. And then what happens is that the current is now what's going to split. Right, so the total current will add up to the sum of the other currents. And we'll dive into that when we talk about Kirchhoff's rules. Okay, there's going to be a junction rule and a voltage rule. Okay, and that's where these really come from. But in both cases, what we can do is we can take all the resistors in the circuit and we can replace it with a single resistor to get the same effect, to make it a simple circuit. And we call that equivalent resistance. Okay, and to find the equivalent resistance for a series circuit, you're just going to simply add up the resistors, right? So I'm going to add up R1 plus R2 plus R3. Now, the parallel circuit is going to be a little bit different because it's going to focus on this inverse. And what you're going to do is you can do 1 over R1 plus 1 over R2 plus 1 over R3, depending on how many circuits you have or how many resistors you have in the circuit. So something to note for series, your equivalent resistance is always going to be greater than the largest. And for parallel, it's always going to be smaller than the smallest resistor. Now, with the parallel equation, I'm going to circle that. Notice that this is 1 over Req, 1 over equivalent resistance. And what that means is that once you have that 1 over R1 plus 1 over R2, you need to flip it. Okay? So your numbers in general should not be decimals. They should be whole numbers or, larger numbers greater than decimals. You'll find there's maybe some case where you do have decimals as an equivalent resistance for parallel, but for the most part, it's going to be something bigger than a decimal. When we do these, kind of just to introduce them, we make the assumption that the battery has no internal resistance, but for the most part, kind of in the real world situation, a battery will have a real world, okay? And so what we call it is the electromotive force. So it's a total energy that be given to a charge leaving the cell and is related to the terminal voltage by an equation. So the electromotive force equation is E, or epsilon, is going to be VT plus IR, okay? So these all equal voltage, So this is the battery voltage, so like 9 volts, right? But this is the voltage caused by the internal resistance. Okay, I know I didn't spell out resistance there, but as you can see, if you see a symbol that looks like that, that means you have internal resistance, right? So you have the resistance caused by the battery, and then you have, the initial, if you want to say what's oftentimes called the terminal voltage. Okay. So now let's look at an equation. Let's look at this in practice. So this is a circuit diagram, and so what they're asking here is simply what is the equivalent resistance of the circuit shown below. All right. So the way we deal with this is first thing we got to do is tackle the parallel circuit part of the circuit, and then that part is in series with R1. So I need to find what is the equivalent resistance that I can replace R2 and R3 with, and then add it to R1 to give me the total resistance, right? So let's deal with the parallel. So I'm going to do 1 over R1 plus 1 over R2. Or sorry, this is going to be R2 and R3. So 1 over R2 would be 1 over 20. R3 is 60, right? And so that's going to end up being a resistance, or 1 over R, right, of 1/15. And then I take the inverse of it. So REQ would be 1 over 15, which tells me that this is going to be 15 ohms. So now I know this is essentially equivalent to 15 ohms. Now that 15 ohm equivalence is in series with the 35 ohms. So now I can find the total equivalent resistance by doing R1, and I'll call it RP for resistance parallel. So it's going to be 35 ohms plus 15 ohms, and it's going to give me 50 ohms. Now, what they could ask now is like, what's the total current in the circuit? So there you would need to know the voltage of the battery, okay? And then you can go from there. They may ask you, what is the voltage across each resistor? What is the voltage, what is the current across each resistor? What is, so there's all things that they can ask at this point in time. But it all starts, right, by finding the equivalent resistance, okay? Now, let's look at this one. So here it's asking, what is the value for R in the following configuration? So they give us the voltage, they give us the amps. So basically what we can do from right now is we can find the equivalent resistance by using Ohm's law. So V equals IR. And this is going to be equivalent resistance because all this VT and VI is going to be total. And so I'm going to say REQ equals V over I, and so it's going to be 20 over 0.8. And so this tells me that my equivalent resistance, right, is going to be, whatever 20 divided by 0.8 is. Apparently I didn't write it down. 25. Okay, so it's going to be 25 ohms. So what that tells me is that REQ is going to be R, which is what I'm looking for, plus the resistance in parallel. So now I have to figure out what is that resistance in parallel by doing 1 over REQ equals 1 over R1 plus 1 over R2. And I may call it 2 and 3 again. Yeah, it's 2 and 3. And so I would say 1 over REQ equals 1 over 30 plus 1 over 60. So that's going to be 3 over 60, or 60 over 3, which is 20, right? Because I just flip them. And so that's telling me that 25 equals R plus 20. And so this resistor in series is equal to 5 ohms. Okay. Again, they may throw in another part saying, hey, what's the voltage across each resistor? What's the current that goes down each resistor? Okay. Very easy. If they ask you the current in that one, it's going to be 0.8. Here, that 0.8 is going to split into whatever value, right? And it will, again, path of least resistance. So least resistance is R2. So I2 would be greater than I3 because there's least resistance for it to travel down, okay? So in the next video, we're going to look at Kirchhoff's rules, okay? So Kirchhoff's rules are very important, especially as we move forward into some of the other more complicated circuits, because you're going to apply these rules. And